So I'm Nithin. I work at Google in their platform security team, and my team focuses on protecting corp endpoints and the operating systems that run on these endpoints. So today I'm going to give a quick talk on firmware security. I like to call it the middle child of security. Ask your middle child why, what that means, right? So yeah, there's this assumption always that I hear that firmware vulnerabilities are really hard to exploit. So, which means that you would need a sophisticated actor like a nation state to exploit it. And that means it's less likely to happen in your organization, right? So you kind of bench it, you put it in your backlog, patch it later, focus on something else, low-hanging fruits, right? So hopefully, by the end of this presentation, I want to break this assumption and maybe get you to dust off some of those old, bugs that you filed against patching these vulnerabilities. So yeah, first let's disambiguate what firmware means. You keep hearing BIOS, firmware, UEFI. What does it all mean? So firmware was the term that was coined in like 1967 in this computer magazine called Datamation, but it's essentially low-level software that runs on low-level components and helps control these small chips, right, on your machine. For example, your Type-C port has a power delivery controller that helps negotiate fast charging for your laptops. Then BIOS, on the other hand, is nothing but firmware that is on your motherboards for compute systems, right? And UEFI, on the other hand, Unified Extensible Firmware Interface, long name. UEFI is a specification that tries to modernize and standardize how more secure firmware is supposed to be implemented, right? So please note that it's not an implementation itself, it's just a specification like an RFC, right? So making a case for firmware security, so I want to highlight three things, right? Why firmware security is important. That is because it is the first piece of code that runs when you turn on your machine. So it's responsible for setting everything up for your operating system, right? So if firmware is bad, it doesn't matter how many security controls you have on your operating system, you cannot trust it. Then the supply chain complexity, right? The amount of players in firmware security supply chain is a lot, and you will see the web of supply chain issues over there. And immediately as a side effect, right? Because the supply chain is so complex, patching becomes not so easy. All right, so let's talk about establishing trust, right? Chain of trust, what does it really mean? So every piece of firmware essentially does two things. First thing it does is that it measures, first thing it does, it verifies if the next piece of firmware or next piece of code that is running is allowed to run or not allowed to run. The second thing it does, it computes the cryptographic hash of this next piece of code, and then it stores it in a register. That's about it. So how it verifies which piece of code is allowed to run, it uses something called DB and DBX, which is like a small list of hashes and signing certificates that either define DB sets what is allowed to run, and DBX is like a revocation list, what is not allowed to run, right? And the measurement is at the bottom. You can see a trusted platform module, which is just like a tiny chip that has registers, and you measure the hash onto it using that formula there, which is essentially you're taking the old value that is already there on the chip, you're computing the new hash, right? And then you're XORing it, and then you're hashing all of it again. So let's start with what happens once you power on a machine, right? You gotta start trust somewhere, as we all know. So the first piece of code that runs is initializes the platform, and it's self-verified, it's self-signed. It has its own problems. We're not going to talk about that today. So after doing that, it's going to run, and it's going to measure its hash into the TPM, right? And then it is responsible, like I said, to verify the next piece of code that is supposed to run. And after verifying that, it's going to, if it's allowed to run, it starts running, right? And again, your firmware execution environment, again, firmware is just not one thing, it's like multiple components, right? So each firmware application gets loaded, it gets verified, it gets measured into the TPM, and then gets run. So this is where things get interesting. So now that your firmware is set up, it's going to pass the baton to your operating system. And basically, it gives the baton to your bootloaders, like Windows Boot Manager or Grub2, to set up the kernel and then set up the user space, right? So it needs to measure, again, do the same thing, measure the bootloader and also verify if it's allowed to run. And OS here, again, uses the same functionality to extend the chain of trust almost to the end, right? So what it does is make sure that every piece of kernel code is, again, verified, signed, and then it also measures it onto the trusted platform module. As you can see in this example, the hashes kept changing, right? So now is where the TPM comes to play. So if you know anything about disk encryption, you know that at the end of the boot stage, you want to decrypt your hard disk, right? And you, or a modern operating system, can seal or like tie the decryption key to a value in the TPM. So the TPM won't decrypt the decryption key if the value does not match a predetermined value. So the value is so sensitive that anything in the boot chain changes, the TPM value won't match. And that's when you see these BitLocker key pop-ups. Anyways, so there you go. Then you essentially reach successful boot, right? Important thing to note here is that the top part is what we know as secure boot, and the bottom part is what usually is called as measured boot. And they work hand in hand. And another thing you can quickly identify is that it can get cumbersome to maintain like all the hashes that are allowed to run in the firmware side, right? You have multiple vendors. Everyone has to maintain their own, hash databases or like certificate authorities, and that's never a good thing. So Microsoft came up with this program where they will verify the firmware for you and then sign it with their signing key. And this certificate is in manufacture time included in the DB by a lot of like vendors. So it's easier, right? It solves all the problem, right? We'll talk about it later. So yeah, now let's move on to supply chain complexity. So like I mentioned, there are a lot of different players, right? First one is original device manufacturers. These people essentially have machinery to print PCBs, print your motherboards, assemble components for you, right? And then you have OEMs themselves who technically might not have the machinery to print motherboards, but they do sell you the machines with the motherboards in them. And you have silicon providers, who come up with the CPUs, right? All the microcode that goes into the CPUs too. And then you have independent BIOS vendors. These are people that specialize in firmware development. These are people that work with all of them and come up with like a BIOS that probably adheres very closely to the UEFI spec. And UEFI there, you can see in between, is a couple of subject matter experts and stakeholders that come up with this specification, essentially. On top of all of this, you have the operating systems themselves, the open source community, and TCG is what defines the specification for TPMs. So yeah, there you have it. So if you were a laptop you want to sell a laptop, right? And what happens? How do you go about it? Probably you don't have your own PCB manufacturing facility. So what you will do is come up with a list of specifications. I want this RAM, I want this size, and everything, right? And then you give these specifications to an ODM, and ODM will choose the best components, print the PCB, and then they go to IBVs, the BIOS vendors, and BIOS vendors will come up with like a BIOS, bare bones firmware for that particular family of machines, right? And they in turn work closely with the silicon providers and even use some open source components like image parsers, for example, in the code base. And then they give that back to you, OEM, and you get to customize things in the BIOS, right? You have Lenovo logo showing up, for example, right? Things like that. And that is the end machine that you get. So now that you've seen the complexity, let's talk about patching. I want to highlight how, because of this long dependency chain, right, the higher up you have a vulnerability, the more impact it has, the harder it's to patch to, because every person after that chain needs to verify the patch and make sure it's not breaking things. So it's a long process. So let's go through like 3 case studies that are slightly relevant. First one is boot hole. Boot hole is a vulnerability in grub2. grub2 is an OS bootloader for mainly Linux distros, right? And it is a buffer overflow vulnerability that you're able to achieve arbitrary code execution. So that's bad. And the important thing to note here is that, remember I told you that it's hard to manage your own certificate authority, so you go to Microsoft and Microsoft will sign the firmware for you. Well, they indirectly sign grub2 too. So what ended up happening is that every machine, it doesn't matter which operating system, any machine that basically trusts this Microsoft certificate is vulnerable to this attack, right? And as you can see there, it took about a year to really update the DBX with the vulnerable hashes. And if you look at it today, if you look at the revocation list, it's public. There are about 177 hashes that are either certificates or actual hashes that have been added associated with this vulnerability into DBX. Logo fail. Yes, logo fail is fairly recent. This is where the vulnerability was up there in the BIOS vendors, right? So BIOS vendors include image parsers, and these image parsers themselves are like verified, signed, right? But apparently, these image parsers can take input that is not verified, like your PNG files or bitmap files. So researchers have found that you can utilize this untrusted code and take advantage of it to execute the vulnerabilities in the parsers, and then so you have like a privileged execution in the firmware space, right? So again, these vulnerabilities, because it was in the BIOS vendor, the impact was much larger, and only a couple of OEMs finally took the patch from the IBVs. BIOS vendors have ended up patching it somewhat, and some of these patches are downstream now, but not all vendors. So it's very likely that your machine probably is vulnerable to this. And now let's talk about BlackLotus. BlackLotus is, I think, one of the first commodity malware that took advantage of a firmware vulnerability. The vulnerability it took advantage of is called baton drop. It basically tricks. It's a vulnerability in Windows bootloader this time, firstly, and it tricks your Windows bootloader to forget about some of the secure boot policy checks for a tiny bit. And when that happens, it's able to execute code that would potentially be blocked and not allowed to execute. During that time, they enroll their own self-signed certificate into the key that'll basically make them persist, even after reimages probably. And they have an executable that runs in the user land too. All it needs is some privileges to turn off a HPCI and BitLocker, and they're good to go. And the thing to note here is that if you look at the timeline, it was obviously MSRC talked about it in Jan 2022, and then the POC dropped around August 2022, right, by the researcher. And then BlackLotus first was identified in VirusTotal around August 23rd. That's about 13 days. That's pretty quick. Then, further right now, Microsoft is, again, they keep, I think, about 200 hashes. They keep banning the vulnerable hashes they find in the wild for the bootloader. But the real thing they need to do is ban the certificate that signs it, right? And it is much more complicated this time because it is not the third-party signing certificate. It's the actual Microsoft signing certificate. So anything, all the kernel, everything can break if it's not done carefully. You can brick your machine. So Microsoft is still doing so. It's in the process. They're yet to announce when they'll enforce this DBX update on your machines, right? So yeah. So where do we go from here, right? I think we as a community should try to work towards eliminating some of these bottlenecks. You can see that DB and DBX updates are like really a big problem here. And there are new things, like I think people have realized that this is an issue. There's secure boot advanced targeting, this new way to like use version numbers instead of actual like signing certificates and hashes to set a minimum version of firmware that is allowed to run, right? Microsoft has that too for BlackLotus now. If you look at the documentation, they're calling it secure version number. I think it's the same thing. Yeah, I'll wrap it up. And the next thing is please hold your OEMs responsible for patching, right? Like logo fail, please reach out to your OEMs and put some pressure on them so they will patch downstream. All right, so this is the initial assumption. And I want to highlight that again, like by making this assumption, you're leaving your fleet or your machine vulnerable for a longer period of time than you think. And hopefully this talk will kind of motivate you. The next time there's a vulnerability, maybe think about it. Think about patching firmware vulnerabilities first. All right, thank you. I'm Nithin Sade, and yeah.